Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into a fascinating paper from ArcSvor, Tiny Pointers, a groundbreaking work in data structures and algorithms. It's really exciting stuff.
I'm eager to hear about it. What's the core idea behind these tiny pointers? Are we talking about, memory savings?
Exactly. The paper introduces a new data structure, the tiny pointer, which, in many applications, can replace traditional log n bit pointers with significantly smaller log n bit pointers. The amazing part is that this only adds a constant factor time overhead. Think of it as getting massive space savings with only a tiny performance penalty.
A constant factor overhead? That sounds almost too good to be true. What's the catch?
Well, there are nuances. The optimal size of these tiny pointers depends on the context. For fixed-size tiny pointers, where all pointers are the same size, the optimal size is theta, log n plus log k bits, where n is the number of elements and k relates to the load factor of the array. For variable-size pointers, where the average size is small but some can be larger, it's theta, log k, expected bits.
Okay, so the size depends on the load factor. Could you elaborate on that? And what are these balls and bins problems they mention?
Right. The load factor represents how full the array is. A higher load factor means more elements are packed into the array, which impacts the efficiency of the tiny pointers. The balls and bins problems are classic problems in probability and combinatorics that the authors had to revisit to develop their optimal tiny pointer constructions. These results are interesting in their own right, even outside the context of tiny pointers. It's a nice example of how seemingly unrelated fields can intersect.
Interesting. So how are these tiny pointers applied? The paper mentions several classic data structure problems.
Yes, they use tiny pointers to improve 5 classic data structure problems: data retrieval, succinct dynamic binary search trees, space-efficient stable dictionaries, space-efficient dictionaries with variable-size keys, and the internal memory stash problem. In each case, they take existing space-inefficient solutions that use traditional pointers and make them space-efficient, essentially for free. It's a powerful technique.
So it's not just a theoretical improvement, it has practical implications for improving the efficiency of existing data structures? That's quite significant. I'm curious, what are the limitations? Are there any scenarios where tiny pointers wouldn't be beneficial?
That's a great question. While the constant factor overhead is generally small, it might become significant in applications where performance is absolutely critical. Also, the space savings are most pronounced when dealing with very large datasets. For smaller datasets, the overhead might outweigh the benefits. It's all about finding the right balance.
I see. So it's a trade-off between space and time complexity, tailored to specific application needs. This is a really elegant solution, though. It's amazing how such a seemingly small change can have such a big impact.
Absolutely. The elegance of the solution, combined with its practical implications, makes this paper a significant contribution to the field. It's a testament to the power of clever data structures and algorithms. And that's all the time we have for today's episode of Tech Bytes and News. Thanks for listening, and we'll see you next time. Goodbye.
Bye-bye.